This is one of the two toughest centrifugal force type problems that you'll see in your homework. It's a pretty difficult problem to set up. Once it gets going though, it's not too hard to solve. This may help you on a particular problem. I don't remember the exact name, but it's a good problem to solve and it's a good one to think about. What we have is a hoop that's spinning around like this. Okay, so if this was the hoop, it's spinning on its axis, which I'd want to demonstrate here. Okay, but it's not CD or anything like that. It's like if you were spinning a hula hoop on a ground like a top. Okay? We have a bead that's on the hoop. And it is going to, when all it's spinning, it's going to slide up. All right? A little bit. Now, keep in mind that it could stay at 0. If it was perfectly balanced, it could stay at 0, it wouldn't go anywhere. But so that's one possible place. But assuming that it's not, and it's going to slide up a little bit until it reaches an equilibrium point. Now we know equilibrium point is the point where the forces are 0. And the net force is 0. And it's going to stay there. The question is at what angle from the center is it going to reach? So, we have to consider the forces that are involved in this. Okay? We know it's spinning in a circle, so we have a centripetal force that needs to be acting. And that's going to be towards the middle direction. We also have a gravitational force that's pulling it downwards. Okay? And finally, we have a force from the wire, which I'm going to call the normal force of the wire pushing it in that direction. Now, you might think these three can't all add up to 0. You're right. What we want is a situation where Fc is the only force left. It's going in a circle. So Fc is going to equal Fn plus Fg. And if you look at the angles of this, if you were to add Fn and Fg together, you'd get straight to the left, which is what we want. Alright, but now let's talk about how they're related. Because right now we've just got this kind of visual relationship between them. The first one is we're going to know that these two are going to be related. Now remember, this is theta here. Okay, so Fg and Fn are going to be related by Fg equaling mg time equals the normal force times cosine of theta. Now typically I think of that as sines usually go theta here, but theta's up there. That's our first thing. And then we also know that Fc is going to equal Fn sine theta. Okay. Unfortunately, we got too many unknowns. We don't know theta, we don't know Fn, we don't know Fc. 2 equations, 3 unknowns. We've got to find one of them somewhere. And that particular one that we can find is Fc. Now, we know Fc is equal to mv squared over r. That's the centripetal force. Now we can find that. We know that r is going to be variable. Okay? R is only going to be 15 centimeters when it's perfectly straight out to the side. We want this r. And that's going to be, okay, 0.15 sine theta. Because this diagonal is going to be 0.15 centimeters. Okay? We also know that omega, okay, is equal to, well, V is equal to omega r. Okay? Which by itself is not helpful, but we know that omega is equal to the number of radians per second. So if we were to take 2 pi, which is the radians in one period, and divide it by the time for one period, we get that omega is 12.57. Excuse me. Now, from that we plug back into here, and we get Fc is equal to m omega squared r. We then plug that back into here, and we get m omega squared r is equal to Fn sine theta. Now we know that r is 0.15 sine theta, so we can get m omega squared times 0.15 is equal to Fn. We now have two equations that we can use. We can substitute for Fn up here, and we get that mg is equal to m omega squared times 0.15 cosine of theta. Our m's cancel, and now everything left is things we know. We know that g is 9.81. We know that omega is 12.57. We're going to square it. We know 0.15, and all we have left is cosine of theta. Eventually we should get that theta is equal to 65.6 degrees. Okay, which means that this theta, this angle here, is 65.6 degrees. And that is the place where it's at equilibrium.